Hi everyone. Here at Caldera Engineering, we specialize in severe service pressure reducing, or often called pressure let down controlled systems. Now I know it's a bit of a mouthful, but hopefully after this video it'll be a lot clearer to you. In our applications, we often come across a specific type of flow called flashing, compressible, and supersonic. This video tells you a little bit more about this specific type of flow and how it impacts our designs. Now you'll also notice that I keep on talking about a let-down system as opposed to a let-down valve, because in severe service, it's more than just a valve. To understand this unique type of flow better, let's look at the first word that describes it: flashing. Flashing happens when a liquid is above its saturation point and out of equilibrium. Some of the liquid turns into a gas. It vaporizes or flashes. Now again, this seemed to be a very difficult concept, but it's actually quite simple. You can have two ways of flashing. You can have a hot liquid under high pressure, and it's within its equilibrium, and then suddenly reduce the pressure that moves it out of its equilibrium. Some of that liquid then rapidly turns into a gas. That is classical flashing, and that's what this video is about. You can also have another type of flashing when you have a liquid at a constant pressure, but you keep on increasing the temperature until it goes out of its equilibrium. It then starts to vaporize. It's a lot milder type of process, and if you haven't guessed it, it's also called boiling. This is not what this video is about. There's also another type of flow that involves flashing. This typically happens if you flow control a hot liquid. Depending on the temperature and the pressure drop over the flow control device, which could be a valve, the liquid can go slightly out of equilibrium. Small amounts of liquid can then vaporize and form small bubbles. After pressure recovery, these bubbles then collapse back into a liquid form. Now this is called cavitation and can be very detrimental to mechanical equipment. I talk about collapsing into a liquid form, but it could be very violent implosions that you can even hear outside of the pipe system. This video is not about this type of flow, but if you're interested, just leave us a comment and we may make a video of this type of flow. Next up is compressible. This is a concept that most people understand relatively well. If you exert a pressure on a material and this material's volume reduces and its density increases, then it's compressible. In short, a solid is incompressible, a liquid is largely incompressible, while a gas is very compressible. That leaves us with supersonic. Supersonic means simply faster than the speed of sound. Now, what you have to keep in mind is that the speed of sound is very much dependent on what medium it travels through. The speed of sound through air is relatively slow, while through a more dense medium like a liquid or a solid, it can be very fast. Now that you know a little bit more about this special type of flow, let's look at a very simple pressure reducing system, and this is as simple as it gets. It is just a pipe that narrows down into a small aperture called the choke point. It then diverges again with increasing diameter before it discharges into a low pressure system. The flow is from left to right, from the high pressure side to the low pressure side. Before the choke point, we essentially have a hot liquid and therefore incompressible flow. It's also subsonic because the speed of sound on a liquid is very high, while liquid linear velocities in pipelines are very low. As the area decreases with a narrowing pipe, the linear velocity of the liquid needs to increase to maintain the same mass flow. The pressure starts to decrease as part of the conservation of energy. It is when the hot liquid reaches the choke point that the interesting thing starts to happen. At this point, the pressure is low enough so that flashing begins. Some of the liquid changes into a gas, and that greatly increases the volumetric flow of the mixture. The linear velocity shoots up, so much so that it actually reaches sonic velocity. At this point in time, the flow is choked. The diameter of this choke point essentially determines the maximum flow that this system can handle. Now, before the choke point, you do not have any flashing because you essentially have an overpressure. But at the choke point where flashing starts, the temperature of the mixture starts to reduce. After the choke point, we now have compressible flow because the majority of the volumetric flow is a gas. It also starts reaching supersonic velocity because the area now starts increasing. The linear velocity continues to increase because there's more and more gas being generated due to the pressure that keeps on reducing. The temperature also reduces, and the mixture is trying to stay in saturated conditions. If this pipe is long enough and wide enough, what will happen is that the pressure will keep on reducing, the linear velocity will keep on increasing, and the pressure will actually be lower than the discharge pressure of the system. At that point in time, we form a shock wave. This shock wave dissipates energy very well. After the shock wave, the linear velocity reduces significantly, and we're now back to subsonic velocities. The pressure also increases to essentially the discharge pressure of the pipe. With the increase in pressure, a small amount of vapor may go back into a liquid form, but the majority of vapor remains as a vapor. The location and characteristics of this shock wave is very important to us here at Caldera. You have to keep in mind that we do not only deal with hot liquids. Majority of application also contains very abrasive solids, and you can just imagine what supersonic flow with an abrasive slurry can do to mechanical equipment. So we need to design the system before the shock wave to be able to handle that type of abrasive high flow conditions, and we need to make sure that this shock wave dissipates enough energy so that it doesn't damage equipment downstream of our pressure reducing systems. I hope you enjoyed the video and now have a better understanding of flashing, compressible and supersonic flow, as well as a pressure reducing system. If you'd like to know more about Caldera engineering or these subjects, please contact us at the contact information below. We would also appreciate your comments regarding this video or any other video you would like us to make. Thank you for viewing.